All right. Thank you, everyone. Good morning, everyone. It's my honor to present our recent work, WINS Multi, a robust asynchronous multi-camera IMU state estimator. I'm Luqi Wang from the Hong Kong University of Science and Technology. So let's start with the motivation of this work. As noted by previous work, visual inertial odometry, VIO in short, can be enhanced by incorporating multiple cameras to acquire more information from the surrounding environment. Most of the recent work have been focusing on asynchronous cameras, while asynchronous cameras with simpler hardware can be can enhance the resilience overlooked. In real applications, especially in demanding environments like wilderness and construction sites, deploying multiple asynchronous cameras can be less cumbersome and offers superior robustness against failures. The key contribution of this work can be summarized as follows. We first develop a novel dynamic feature number allocation alongside a frame priority coordination strategy to improve the front end. We then combine the parallel front-end and customized optimization-based backend into a robust multi-camera IMU state estimator that can accommodate multiple asynchronous cameras of mixed types. We finally integrate the estimator into a quadrilateral platform for extensive experiments in realistic and challenging scenarios. The system architecture is illustrated here. So first, the parallel visual front-end acquires images from respective camera modules to perform feature detection and tracking asynchronously, and the processed measurements are subsequently coordinated by the front-end coordinator. Then the coordinator dynamically redistributes the number of features processed by each front-end based on the collective features, as well as determines whether the measurements are forwarded to the sliding window in the backend optimization module according to the priority. And finally, the backend obtains the visual and depth measurement, as well as pre-integration results from the raw IMU input to output the camera and IMU rate odometries after optimization. So after the overview of the system architecture, let's talk about the technical details starting from the asynchronous parallel front-end. So the front-end extracts and tracks features in parallel, and each camera or IMU module is assigned with an individual thread. Then the asynchronous measurements are inserted into a state history buffer and chronologically ordered according to the timestamp. You can see on the right, it is a screenshot of the feature extraction and tracking result using 3 cameras simultaneously. And as demonstrated below, it is possible that a frame with an earlier timestamp arrives later. Hence, we need to maintain a state history buffer to handle this issue. And then let's talk about the details about the front-end coordinator. So the coordinator firstly dynamically allocates the maximum feature number of each camera FNI according to the tracked feature number TFNI from the last frame, given a total maximum feature number capital FN, so that the feature tracking rate converges to the same across cameras. So on the right, you can see that the proposed method dynamically allocates the maximum feature number of each camera, which is shown on the top left corner of each tracked image. So and this is according to the tracked feature number, and this uses the features more efficiently. Then the frame priority coordinator handles the priority among the cameras to make the efficient use of the computation's resources and preclude partial camera failures. It accepts the frame with either the highest feature priority, which is a frame with the most allocated features to maintain consistent feature tracking quality, or the highest exponential decay time priority to preclude camera failures. So after a frame is accepted by the frame coordinator, the corresponding measurements are fed to the backend for optimization. The optimization problem is similar to the state-of-the-art method, which optimize states in a sliding window, while some details are different. The states consist of poses, velocities, IMU biases, inverse feature depths, camera extrinsic parameters, and camera IMU time differences. The optimization objective is to minimize the combination of the prior factor from marginalization, IMU propagation factor, and the visual or depth factor if an RGBD camera is adopted. You can see from the illustration on the right, one of the major differences from the synchronous camera systems is that the frame number from each camera is not necessarily to be the same in the sliding window. And another main difference from the synchronized camera is the marginalization strategy. Upon the arrival of a new frame from camera I, you can see from the illustration, the last frame from camera I is checked. If it is a keyframe, the most outdated frame in the sliding window is marginalized, regardless of the originating camera. And otherwise, the last frame from camera I is thrown. This strategy is able to handle uneven frames from multiple cameras and cope with the malfunction of certain cameras. And finally, I would like to talk about the experiments and results. The proposed Vince multi is compatible with mixed types of monocular, RGBD, and stereo camera modules. And we conduct application studies on the drone with two configurations. Three on the left, the three RGBD cameras. On the right, the two RGBD cameras with one stereo camera. And the three cameras facing the front, top, and down. And the experiments are conducted in this wall inspection environment. So first, let's see the comparison of the proposed three RGBD camera system with single front camera in a wall inspection scenario. We can see that when the drone takes off facing the black wall, there is a scarcely usable feature on the wall. When only using the front camera, the odometry drifts severely, while when using three cameras, the system can still use the top and bottom cameras to achieve promising state estimation results. A similar phenomenon occurs when facing the opposite white wall. We can see from the final trajectory result, the state estimation using the front camera drifts severely when while the proposed is very close to the ground truth from motion capture system. Here's a snapshot of the feature image at the circle position. You can see in the middle. During the takeoff facing the black wall, we can see that no matter how many features on the wall are extracted, they are not usable. And the proposed method not only use the information from other camera, but also use the features more efficiently by allocating less feature number to the front camera. And another ablation study is on the dynamic feature allocation strategy. So in this experiment, we replace the top RGBD camera with a stereo camera. The proposed method dynamically allocates maximum feature number, while the ablation experiment constantly allocates equal features to each camera. The total maximum number of feature number of two configurations are the same. We can clearly see a severe drift of the estimated odometry on the ablation group, while the proposed method maintains a good performance. So here's a snapshot of the feature image as the circle facing the white wall. We can see that since the features on the white wall are not useful, the proposed method allocates more features to the top and bottom cameras to maintain more stable feature tracking. So this demonstration shows the effectiveness of the proposed dynamic feature allocation strategy. And to validate the robustness of the proposed system, which is crucial during the real applications, we also conduct a camera failure and recovery test. So firstly, we let the drone take off with only the top and bottom camera. And then we block the top camera with the lid and the drone flies with only the bottom camera. And then we remove the lid and the drone can use both the top and bottom camera to fly. And after that, we unplug the top camera. Then the drone is still able to fly on the bottom camera. And finally, we plug the front camera so that and the drone is able to use both the bottom camera and the recover front camera to fly and also land. And here we show the benchmark results on the estimated trajectories of the proposed method using three cameras. The ablation of dynamic feature allocation and using single cameras. We can see that the proposed method using 3 cameras performs best in all the 3 experiment scenarios. And the efficacy of and robustness of the proposed method are further validated during the complex task of aerial vent pipe inspection. This is a vent pipe with 0.7 diameter, and the camera position is shown using arrows. All the computations are performed on the onboard computer. We can see that the state estimation using the proposed method successfully supports this application. And we also conduct another inspection in a more challenging rectangular vent pipe. This vent pipe has a dimension from 0.5 meter to 0.8 meter, and the camera positions are also indicated using the arrows. So despite the dark and narrow environment, by adopting the auxiliary LED, the drone is still able to localize itself using the proposed state estimation method. And the estimation successfully supports the mapping and planning during this challenging application. So the functionality in these challenging scenarios proves the effectiveness of the proposed method and robustness of the system, and further implies the practicability of the system in real applications. So that's all. Thank you.
Thank you very much for the great presentation. Due to the sake of time, we'll have to quickly move on to our second presentation. Thank you.